Have you ever felt like time is flying by, or maybe dragging on forever? Well, what if I told you that's not just a feeling? Time actually moves at different speeds depending on where you are. It sounds like science fiction, but it's a mind-bending reality of our universe. Today, we're going on a journey to understand why your watch ticks differently than a clock in space. Let's start with a name you definitely know, Albert Einstein. Over 100 years ago, Einstein turned our understanding of the universe upside down with his theories of relativity. Before him, everyone, including scientists like Isaac Newton, thought of time as this absolute, constant river flowing at the same rate for everyone, everywhere. It was the universe's master clock. But Einstein came along and said, not so fast. He proposed that time is not separate from space. Instead, they are woven together into a single four-dimensional fabric he called space-time. Imagine a giant, stretchy sheet of fabric. That's space-time. Now, if you place a heavy bowling ball in the middle of it, what happens? The fabric curves and dips around the ball. This is exactly what massive objects like planets and stars do to space-time. They warp it. And here's the kicker. This curvature of space-time is what we experience as gravity. So, gravity isn't a mysterious force pulling things together. It's the shape of the universe itself, telling objects how to move. This is where things get really interesting for our clocks. Einstein's theory of general relativity predicts that the stronger the gravity, the slower time passes. This effect is called gravitational time dilation. Think back to our stretchy fabric. The closer you are to that heavy bowling ball, the deeper you are in the curve. For time, this means it has to work harder to climb out of that gravitational well, so it slows down. So, if you were standing near a supermassive black hole, where gravity is incredibly intense, time for you would pass much, much slower than for someone far away in space. While you might only experience a few hours, years or even centuries could have passed for the rest of the universe. It's a concept that filmmakers love, and for good reason. It's a real, measurable phenomenon. Now, you might be thinking, okay, that's cool for black holes, but does this actually affect us here on Earth? The answer is a resounding yes, and you probably use the proof every single day. I'm talking about the GPS on your phone. The Global Positioning System, or GPS, works by using a network of about 31 satellites orbiting the Earth. These satellites are way up there, about 20,000 kilometers above the surface. At that altitude, Earth's gravity is significantly weaker than it is down here where we live. According to Einstein's theory, because the gravity is weaker, time for those satellites should tick slightly faster than our clocks on the ground. And it's not a tiny, insignificant amount. The clocks on GPS satellites run ahead of ground clocks by about 45 microseconds every single day. Now, 45 microseconds, that's 45 millionths of a second might sound like nothing. Who cares about such a small fraction of time? Well, your phone's GPS cares a lot. GPS calculates your location by measuring the time it takes for signals to travel from multiple satellites to your device. To get your position right, these time measurements need to be incredibly precise. Light travels at about 300,000 kilometers per second. So, if your GPS timing is off by just 45 microseconds, the calculated position would be wrong by about 13.5 kilometers. Every single day, your location would drift by more than 13 kilometers. Imagine trying to get directions to a new coffee shop and ending up in a different neighborhood entirely. It would make GPS completely useless. To prevent this, the engineers who designed the GPS system had to account for Einstein's theory of relativity. The clocks on the satellites are deliberately built to run slightly slower. Once they're in orbit, the weaker gravity causes them to speed up, perfectly syncing them with clocks on Earth. It's an amazing, everyday application of a theory that once seemed purely abstract. But wait, there's another layer to this. It's not just about gravity. Einstein's other theory, special relativity, also plays a role. Special relativity deals with the relationship between space and time for objects moving at constant speeds. One of its key predictions is that the faster you move, the slower time passes for you relative to a stationary observer. This is another form of time dilation. Our GPS satellites aren't just sitting still up there. They're zipping around the Earth at about 14,000 kilometers per hour. That's fast. Because of this high speed, special relativity predicts their clocks should tick slower than ours on the ground by about 7 microseconds per day. so we have two competing effects. General relativity, due to weaker gravity, speeds up the satellite clocks by 45 microseconds a day. Special relativity, due to their high speed, slows them down by 7 microseconds a day. When you do the math, the net effect is that the satellite clocks run faster than ground clocks by 38 microseconds each day. 45 minus 7 equals 38. And it's this 38 microsecond difference that engineers have to correct for every single day to keep our GPS accurate. Without Einstein, your Uber driver would never find you. So, we've established that time is relative. It depends on your gravity and your speed. What does this mean for the future, especially for space travel? It means we're going to have to get really good at timekeeping. Imagine sending astronauts on a long mission to Mars. They'll be traveling at very high speeds and will be in a different gravitational environment than us on Earth. Their clocks will tick at a slightly different rate. For a round trip to Mars, the time difference might only be a few milliseconds. Not a huge deal. But what about more ambitious missions? Let's dream bigger. What about a trip to our nearest star system, Proxima Centauri, which is about 4.2 light-years away? Even if we could build a spacecraft that travels at, say, 20% the speed of light, the journey there and back would take over 40 years from the perspective of people on Earth. But for the astronauts on board, thanks to time dilation, only about 39 years would have passed. They would return to Earth slightly younger than if they had stayed home. Push it even further to near the speed of light, and the effects become dramatic. If you could travel at 99.9% the speed of light, you could journey thousands of light years across the galaxy in what feels like only a few years of your own life. But when you return to Earth, you'd find that tens of thousands of years had passed. Everyone you knew would be long gone. The world would be completely unrecognizable. You would have effectively traveled into the future. This isn't just a fun thought experiment. It's a fundamental challenge for interstellar travel. How do we coordinate with missions that are experiencing time differently? How do we manage the psychological impact on astronauts who return to a world that has moved on without them? These are questions that future generations of scientists and explorers will have to answer. The fact that time is not absolute is one of the most profound discoveries in human history. It shifted our entire perception of reality. It shows us that the universe is a much stranger and more wonderful place than we ever imagined. From the GPS in your pocket to the dreams of traveling among the stars, Einstein's legacy is all around us, constantly reminding us that our everyday experience is just one small slice of a much grander, more complex cosmic reality. So next time you look up at the night sky, remember that you're not just looking at distant points of light. You're looking across vast stretches of space and time, a universe where every clock ticks to its own beat, all dancing to the rhythm of gravity and motion. Thanks for joining me on this journey through space-time. If you enjoyed this mind-bending exploration, make sure to hit that like button and subscribe for more deep dives into the mysteries of our universe. Let me know in the comments what cosmic question you want us to tackle next. See you in the next video.